Before there were stars or planets, there was a single point containing everything. This is the story of how something came from that nothing, the origin of the universe's very first particles. We are about to explore 30 mind-bending theories that attempt to explain what those primordial building blocks were and how they sparked into existence. By the end, you will possess a new framework for understanding the cosmos itself. We will question if our universe is unique and what existed before time began. What do you believe sparked our entire reality into being? The most foundational story of our beginning starts with a singularity. This was not merely a point in space, but the point. All the energy, all the potential for every star and galaxy, every particle that would one day form you and me, was compressed into an infinitely dense, infinitely hot speck. The very laws of physics as we know them did not apply here. They broke down, ceasing to exist in a state of such extreme conditions. Then an event occurred that we call the Big Bang. It was not an explosion into space, but rather the rapid expansion of space itself. In the first fleeting moments, the universe was a searing, opaque soup of pure energy, far too hot for any solid structures to exist. But as it expanded, it cooled, and in that cooling, a profound transformation began. Energy began to condense, flickering into the very first particles of matter. Think of steam cooling on a window pane and turning into droplets of water. In a similar, yet vastly more fundamental way, the raw energy of creation began to crystallize into something tangible. This was the moment the first seeds of reality were sown, the stage set for everything that would ever follow. But this initial expansion was just a prelude to something far more dramatic. A fraction of a second after everything began, the universe underwent a growth spurt of unimaginable proportions. This is the theory of cosmic inflation proposed by physicist Alan Guth. Picture the universe still smaller than a single atom, suddenly doubling in size, then doubling again and again, in intervals so brief they are almost impossible to describe. This was not a gentle swelling. It was a violent, exponential explosion of space itself, far faster than the speed of light. In less than a blink of an eye, a subatomic speck was stretched to a size larger than our entire observable universe today. Why does this matter? Because this incredible inflationary surge solved some of the cosmos's deepest puzzles. It ironed out the universe, smoothing it from a potentially lumpy, chaotic mess into the remarkably uniform expanse we observe in the cosmic microwave background. Yet it was not perfectly smooth. On the smallest quantum scales, tiny fluctuations were inevitable. As space inflated at a staggering rate, these minute ripples were stretched to enormous sizes. These imprints, frozen into the fabric of the cosmos, became the gravitational seeds for everything to come. The slightly denser patches would eventually pull in more matter over billions of years, giving rise to the vast cosmic web of galaxies and galaxy clusters. All of this structure was born from quantum whispers, amplified to a cosmic roar by inflation, all before a single stable particle had even taken shape. Yet before even inflation could begin, we must venture into a realm of even greater mystery. This is the Planck epoch, the very first conceivable slice of time. From the moment of the Big Bang until 10 to the power of -43 seconds had passed, the universe was in a state that defies all modern physics. To grasp this scale, consider that a single second contains more Planck times than there have been seconds since the Big Bang itself. In this primordial instant, the cosmos was so incredibly hot and dense that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were not separate at all. They were fused into one single, unified superforce. The very fabric of space and time as we understand them did not exist here. They were likely born from this chaotic, seething froth, a concept we call quantum foam. Within this foam, the idea of a particle, a distinct point-like object, becomes meaningless. Reality itself was a turbulent sea of potential, where energy and space-time were inextricably linked and constantly fluctuating. What we call the first particles may not have been objects at all, but rather transient knots or vibrations in this fundamental geometry. This is the ultimate frontier of our knowledge, a point where our current theories simply break down and the true origin of everything remains shrouded in a brilliant, impenetrable light. As the universe expanded beyond that first unimaginable moment, a new chapter began. The Planck epoch gave way to a slightly more familiar, yet still alien, reality. This was the Grand Unification epoch, a period where the cosmic rulebook started to take its earliest form. The first and most dramatic separation had already occurred. Gravity, the force that would one day sculpt galaxies and bend starlight, peeled away from the other three fundamental forces. It began its own solitary journey through the fabric of space-time. But what remained was still a single, powerful entity. For a fleeting time, the strong nuclear force which binds atomic nuclei together, the weak nuclear force responsible for radioactive decay, and the electromagnetic force which governs light and chemistry were not distinct. They were fused into one unified superforce. This is the heart of what physicists call grand unified theories, or GUTs for short. These theories attempt to describe this brief, harmonious period where three of nature's forces were, in essence, different facets of a single, elegant interaction. This unity could not last. As the infant universe continued to cool and expand, this perfect symmetry was destined to break. Think of it like water. At high temperatures, water is a uniform liquid, its molecules moving freely. But as it cools, it undergoes a phase transition, crystallizing into the structured symmetry of ice. In a similar cosmic upheaval, the universe cooled past a critical threshold, and the grand unified force shattered into the three separate forces we recognize today. This violent breaking of symmetry is believed to have unleashed a torrent of raw material. It may have been the forge that created the universe's very first true particles. Among the most significant were hypothetical particles predicted by grand unified theories known as X and Y bosons. These are not the stable particles that make up our atoms today. They were incredibly massive and unstable, existing for only a sliver of a second. Yet in their brief lives and rapid decay, they may have performed a crucial act. Their interactions are thought to have tipped the cosmic scales, creating a tiny, fundamental imbalance between matter and antimatter. For every 10 billion antimatter particles, there might have been 10 billion and 1 matter particles. When matter and antimatter subsequently annihilated each other in a blaze of pure energy, that one particle in 10 billion was left over. That infinitesimal surplus is everything we see around us. Every star, every planet, every one of us is made from the leftover debris of that ancient, broken symmetry, the echo of particles that vanished almost as soon as they were born. This broken symmetry set the stage for a new and equally alien reality. The universe was now a seething ocean, not of energy but of something more tangible. For the first few microseconds of existence, all of creation was a hot, dense quark gluon plasma. In this primordial state, the fundamental building blocks of matter as we know them were utterly liberated. Quarks, the particles that would one day compose protons and neutrons, could not bind together. They roamed freely, like individual ingredients in a cosmic soup that was far too hot to ever solidify. Gluons, the particles that carry the strong nuclear force, were constantly exchanged between these free quarks, creating a frenzied, chaotic dance. This was not a gas or a liquid in any ordinary sense. It was a unique phase of matter, a perfect, frictionless fluid where the very concept of an individual particle was almost lost in the collective frenzy. You could not find a single proton or neutron in this environment. The temperature was so immense, trillions of degrees, that the powerful force that normally locks quarks together was rendered impotent. Any attempt by quarks to pair up was instantly torn apart by the sheer, violent energy surrounding them. This quark soup was the dominant state of all matter, the universal canvas upon which everything else would be painted. But this could not last. The relentless expansion of the universe meant it was constantly cooling. As the temperature plummeted past a critical threshold, a profound transformation swept across the cosmos. It was a phase transition, like steam condensing into water. Suddenly, the strong nuclear force gained the upper hand. The free-roaming quarks and gluons found themselves pulled into permanent partnerships. Quarks bound together in groups of 3, forming the first stable protons and neutrons. The universe had finally graduated from a formless, energetic soup to a state containing the recognizable seeds of atomic nuclei. In a sense, this was the moment the first true matter was forged, locking the building blocks away into the particles that would go on to construct our entire world. This great cosmic forge where quarks first bonded marks the dawn of the Hadron Epoch. For a fleeting few moments, the universe was a frantic factory, assembling the very first composite particles. Quarks, once free and wild, were now captured by the powerful strong force, locking together in groups of 3. These new structures were the hadrons, a family that includes the familiar protons and neutrons that form the hearts of all atoms. But this new era of structure was also a time of immense destruction. The universe was still a blistering maelstrom, teeming with matter and its mysterious twin, antimatter. For every proton born, an antiproton was also created. For every electron, a positron. Matter and antimatter are perfect opposites, and when they meet, they do not simply push apart. They annihilate each other in a flash of pure, radiant energy, vanishing completely. And this is precisely what began to happen on a scale that is almost impossible to comprehend. A great annihilation swept through the cosmos. Most of the matter that had just condensed into existence was suddenly meeting its antimatter counterpart, and together they were turning back into light. It was the single most destructive event in the history of the universe, undoing almost all of the work of creation in an instant. Why, then, is there anything left at all? This is one of the deepest mysteries in all of physics. Somehow, during those earlier moments of broken symmetry, a tiny, almost imperceptible bias had been baked into the laws of physics. For every 10 billion antiprotons, there were 10 billion and 1 protons. For every 10 billion positrons, 10 billion and 1 electrons. When the great annihilation finished, when all the particle-antiparticle pairs had found each other and vanished, that 1 in 10 billion surplus remained. That minuscule excess is everything. Every galaxy, every star, every planet, and every one of us is made from that 1 part in 10 billion leftover. We are the survivors of the greatest battle in cosmic history, the silent remnant of an annihilation that nearly returned the entire universe to a state of pure, featureless light. From the ashes of the great annihilation, a new era dawned. With most of the hadrons gone, the universe became a stage for a different kind of actor. This was the Lepton epoch, a time dominated by particles far lighter and more elusive than protons or neutrons. These were the leptons, a family that includes the familiar electron and its mysterious, ghostly cousin, the neutrino. For a while, the universe was a dense, hot fog of these particles, constantly colliding and interacting with the remaining photons in a frantic, energetic dance. Electrons and positrons, the antimatter counterparts of electrons, were constantly being created from pure energy and then annihilating each other back into light, maintaining a delicate, seething equilibrium. But the relentless expansion and cooling of the cosmos would soon break this balance as well. As the temperature dropped further, the energy of the photons was no longer sufficient to spontaneously create new electron-positron pairs. A second, quieter annihilation occurred. Nearly all the electrons and positrons found each other and vanished, leaving behind only the tiny surplus of electrons that matched the surplus of protons from the previous era. This ensured that the future universe would have a balance of positive and negative charges, allowing for the formation of stable atoms. Yet, the most profound event of this epoch involved the neutrinos. Up until this point, these nearly massless particles had been trapped, constantly bumping into other matter in the thick cosmic soup. But as the universe expanded to a specific, critical size, something remarkable happened. The density of matter dropped so low that neutrinos simply stopped interacting with everything else. In an instant, they went from being active participants to silent, ghostly spectators. This moment is known as neutrino decoupling. Trillions upon trillions of these particles suddenly broke free and began streaming across the universe, never to significantly interact with matter again. They still exist today, forming a cosmic background of neutrino radiation that permeates all of space, a fossil record even older than the cosmic microwave background. Every second, billions of these ancient neutrinos from the Lepton epoch are passing through your body completely unnoticed, a silent whisper from the universe's first moments. With the chaos of annihilation finally over, the universe settled into a new, simpler state. For the next few minutes, it became the most immense nuclear reactor imaginable. This brief but crucial window is known as Big Bang nucleosynthesis, the process that forged the very first atomic nuclei. The ingredients were now in place, a sparse sea of protons, neutrons, and electrons, all swimming in a brilliant bath of light. The temperature, though still incredibly hot, had finally dropped enough for something miraculous to happen. Protons, which are simply lone hydrogen nuclei, could now capture neutrons. When a proton and a neutron managed to collide and stick together, they formed a new, heavier nucleus called deuterium. This was the critical first step. For a short time prior, the universe had been too hot for deuterium to survive. Any time a deuterium nucleus formed, it was immediately blasted apart by a high-energy photon. But as the cosmos cooled past a specific point, this photon barrier was finally overcome. Deuterium became stable, acting as a crucial stepping stone. Once deuterium was available, a cascade of fusion reactions began. Deuterium nuclei could collide with each other or with additional protons and neutrons, building up heavier elements. The main product of this frantic 3-minute fusion frenzy was helium. For every 12 or so hydrogen nuclei, one helium nucleus was created. Trace amounts of the next lightest element, lithium, were also forged. And then, just as suddenly as it began, it was all over. The universe had expanded and cooled so much that the particles were now too far apart and moving too slowly to overcome their mutual electrical repulsion. The cosmic reactor shut down. This abrupt halt left a very specific cosmic fingerprint, a primordial composition of about 75% hydrogen and 25% helium by mass, with just a tiny sprinkling of lithium. Every star and galaxy that would ever form began with this exact same elemental recipe. The iron in your blood, the oxygen you breathe, the calcium in your bones, none of that existed yet. Those heavier elements would have to wait for the violent lives and deaths of the first stars. All the complexity to come was built upon this simple, elegant foundation, the raw ingredients cast into the expanding dark during the universe's first few minutes. The cosmic inflation that smoothed our infant universe might not have been a one-time event. According to some interpretations, it could be a process without end, a theory known as eternal inflation. Picture the fabric of space-time not as a single, expanding balloon, but as an endlessly boiling cosmic pot. In most regions, inflation ends, just as it did for our observable universe, allowing for the formation of stars and galaxies. But in between these calm pockets, the inflationary energy field continues to repower itself, stretching space at an exponential rate forever. Within this eternally inflating background, random quantum fluctuations can trigger the formation of new, self-contained regions where inflation locally stops. Each of these regions becomes a separate bubble universe, budding off from the eternal inflationary sea. Our entire cosmos, with all its hundreds of billions of galaxies, could be just one such bubble in an infinite, frothing multiverse. The profound implication is that the conditions inside each bubble are set randomly when it forms. The fundamental constants, the strength of gravity, the number of spatial dimensions, even the types of fundamental particles that can exist could all be different. In one bubble universe, the weak nuclear force might be so strong that stars burn out in an instant. In another, quarks might never have combined into protons, leaving a universe devoid of atoms as we know them. This means the first particles that emerged in our universe, the specific quarks and electrons that built our reality, were not a unique or inevitable outcome. They were simply the winning ticket in a cosmic lottery of unimaginable scale. The fact that our universe has the right particles and forces to allow for complex structures, and ultimately for us, is not a designed miracle but a statistical necessity. In an infinite multiverse, every possible combination of physical laws must arise somewhere. We simply exist in one of the rare bubbles where the conditions were just right for life to eventually emerge and ponder its own origins. But what if the very idea of a particle is an illusion? What if the true nature of reality is not a collection of tiny dots but something far more elegant? This is the radical proposal of string theory, a framework that rewrites the first moments of the universe. It suggests that the most fundamental building blocks are not zero-dimensional points, but unimaginably small, vibrating loops of energy. These are strings. To grasp their scale, picture a single atom. Now magnify its nucleus. A string would be to a proton what a tree is to our entire solar system. These are not physical threads you could ever see or touch. They are one-dimensional rips in the fabric of space-time itself, and their behavior dictates everything. A string is not a particle in itself, it is the potential for a particle. The magic lies entirely in its vibration. Think of a guitar string. Pluck it one way and it produces a specific musical note. Pluck it differently and you get another note. The string itself is the same, but its vibrational pattern defines the sound. In string theory, this concept is applied to the very foundation of reality. One specific vibration pattern might correspond to an electron. A different, more energetic resonance could create a quark. Another distinct hum might manifest as a photon, the particle of light. In this breathtaking vision, every single type of particle in the universe, every force carrier, is just a different resonant note played on the same fundamental strings. This offers a profound unification. The chaotic zoo of particles and the forces that govern them are no longer separate, unrelated entities. They are all different melodies emerging from the same cosmic instrument. For the very first particles, this means they were not born from a random condensation of energy. They were the first vibrational modes to stabilize as the universe cooled from the Big Bang, the primal harmonics that defined the earliest structures of matter and force, all woven together from the very beginning. Yet string theory's elegant symphony of vibrating strings leads us directly to another profound idea. Supersymmetry is a theory so beautiful that many physicists feel it simply must be true. It proposes a deep and hidden kinship between the two great families of particles, the fermions and the bosons. Fermions are the building blocks of matter, like quarks and electrons. Bosons are the force carriers, like photons and gluons. In our everyday world, they seem completely distinct. But supersymmetry suggests that at the incredibly high energies of the early universe, this division blurred into nothing. For every known fermion, there should be a superpartner boson. For every known boson, a superpartner fermion. This would double the number of fundamental particles in existence. An electron, a fermion, would be paired with a selectron, a boson. A photon, a boson, would be paired with a photino, a fermion. This symmetry is not just a mathematical curiosity. It solves some of the most nagging problems in modern physics. It provides a perfect candidate for the mysterious substance known as dark matter. The lightest of these superparticles, often called the neutralino, would be stable, electrically neutral, and would barely interact with ordinary matter, exactly matching the profile of dark matter. In the first frantic moments after the Big Bang, the universe was a seething, high-energy arena where these superpartners would have been abundant and active. They would have collided, decayed, and shaped the evolution of the cosmos in ways we are only beginning to understand. The fact that we do not see these particles today is not proof they do not exist. It simply means that as the universe cooled, the symmetry broke. The superpartners became incredibly massive, too heavy to be produced in any particle accelerator we have yet built. Their existence remains a ghostly signature in our equations, a prediction waiting for a universe of evidence to confirm. Finding even one would be a window into that primordial, symmetric state, revealing a cosmos far more interconnected and harmonious than it appears. The elegant symmetries of string theory hint at a reality far stranger than we can perceive. This leads us to a concept that challenges the very nature of dimensionality itself. The holographic principle proposes that our universe, with its rich three-dimensional tapestry of galaxies, stars, and people, is not fundamentally three-dimensional at all. It may be a hologram, a vast and incredibly detailed projection of information encoded on a distant, two-dimensional surface. Think of a credit card hologram, a flat sticker that creates the illusion of a three-dimensional image. The holographic principle suggests our entire cosmos operates on a similar, but vastly more profound scale. The information describing every particle, every force, and every event within our universe could be stored on a thin shell at the cosmic boundary, like data etched onto the surface of a giant bubble. If this is true, then the first particles were not the true foundation of reality. They were merely the projected image of a far more fundamental process, a computation happening on the edge of space. Their properties, their interactions, and their very existence were consequences of bits of information being processed on that lower dimensional screen. This transforms our search for the first particles from a hunt for fundamental objects into a deciphering of a cosmic code. The origin of everything we see and are may not lie in a singularity of energy, but in a singularity of information, a foundational layer of reality where the universe is ultimately written in ones and zeros on the fabric of spacetime itself. While string theory weaves a symphony of vibrating strings, another profound idea offers a completely different vision of reality's foundation. Loop quantum gravity proposes that space and time are not smooth and continuous as Einstein described. Instead, they are woven from a fabric of tiny, discrete, indivisible threads. These are loops, the atoms of space itself. Picture the universe not as a seamless sheet, but as an incredibly fine mesh, a cosmic network where each intersecting thread defines a tiny volume of space. There is no such thing as an infinitely small point in this theory. Space comes in a smallest possible unit, a quantum of volume, just as light comes in indivisible packets called photons. This radical rethinking of geometry has a stunning consequence for the origin of everything. If space is made of finite grains, then it cannot be compressed into an infinitely dense singularity. The Big Bang was not the beginning from nothing but a transformational event. The mathematics of loop quantum gravity describes a universe that, when run backwards in time, does not collapse to a point. Instead, the dense mesh of space reaches a maximum density and then rebounds. This is the theory of the Big Bounce. Our entire cosmos, with its billions of galaxies, may have been born from the collapse of a previous universe. In this grand cosmic cycle, the first particles of our era were not created from nothing. They were reborn. As the previous universe contracted in a great crunch, all matter and energy were compressed to an unimaginable density. At the moment of the bounce, the immense gravitational energy of that collapse was transformed, fueling the expansion of our new universe and repopulating it with a fresh wave of fundamental particles. We are not the first chapter in the story of existence, but merely the latest verse in an endless cosmic poem, with particles and space itself eternally recycling through cycles of collapse and rebirth. While the Big Bounce offers a cyclic rebirth within our own dimensions, another theory proposes our entire universe was forged in a collision of cosmic membranes. This is the ekpyrotic universe scenario, a name derived from the Greek word for conflagration. It envisions our reality as a three-dimensional surface or a brain floating within a higher dimensional space known as the bulk. We are not alone in this vast expanse. Other brains, other universes could be drifting nearby in the hidden dimensions. The story of our beginning starts not with a singularity, but with a slow gravitational dance. A neighboring brain, a parallel reality, gradually moved closer to ours over an immense period. This was not a head-on crash, but a gentle, glancing collision. Yet the energy released by this contact was astronomical. The kinetic energy of the impact was instantly converted into an intense, uniform heat, flooding our brain and creating the hot, dense state we identify as the Big Bang. In this model, the Big Bang was not the absolute beginning, but a violent phase transition. The first particles of our cosmic cycle did not condense from nothing. They were ignited from the raw energy of this interdimensional contact, a spark struck from the friction between two worlds. This collision also provides a natural explanation for the uniformity we see in the cosmic microwave background. Because the brains collided across their entire surfaces simultaneously, the energy was deposited evenly everywhere at once, eliminating the need for a period of rapid inflation to smooth everything out. Our universe, with all its galaxies and particles, is simply the aftermath of a grand cosmic encounter, the echo of a collision in a realm of higher dimensions we cannot yet perceive. Yet another vision of a cyclical cosmos offers a truly mind-bending perspective. Roger Penrose's conformal cyclic cosmology proposes that our universe is not the first, nor will it be the last, in an infinite chain of cosmic epochs he calls eons. In this profound model, the end of one universe becomes the beginning of the next in the most elegant way imaginable. As our own cosmos expands toward its ultimate fate, all matter will eventually decay or be pulled apart, and black holes will evaporate through Hawking radiation. What remains is a universe of almost pure, featureless energy, populated only by massless particles like photons and gravitational waves. At this point, something extraordinary happens. The universe becomes so vast and empty that the concept of scale loses all meaning. A single wavelength of light becomes stretched across the entire cosmos. In this state of infinite dilution, the universe effectively forgets its own size. Through a complex mathematical transformation known as conformal rescaling, this vast, cold, empty end is geometrically identical to a hot, dense, small beginning. The final, faded whisper of one eon is seamlessly reborn as the fiery shout of the next Big Bang. The first particles of a new eon are not created from nothing. They are the direct descendants of the previous universe's final radiation. The photons and gravitational waves from the death of one cosmos are transformed through this cosmic reset into the initial energy and particles that fuel the next. In this eternal return, the very first structures to form in a new eon are not random quantum fluctuations, but the imprints of gravitational waves from the collisions of supermassive black holes that died trillions of years prior in the old eon. We may even be able to see the faint echoes of that previous universe in the cosmic microwave background, a ghostly signature of a cosmos that existed before our own. This means the building blocks of our reality are cosmic ghosts, recycled remnants from a time before time, in an endless, timeless cycle of transformation. But this endless cosmic cycle still leaves a fundamental question unanswered. Where did the very first universe come from? The most radical answer physics can offer is that it came from nothing at all. This is the startling implication of quantum fluctuations. In our everyday world, we think of a vacuum as pure emptiness, a void completely devoid of anything. But in the quantum realm, a vacuum is a seething, chaotic place. The Heisenberg uncertainty principle tells us that we can never know both the exact energy and the exact duration of a system simultaneously. This allows for a bizarre loophole in the laws of physics. For incredibly brief moments, energy can be borrowed from nowhere. This borrowed energy manifests as pairs of virtual particles, a particle and its antimatter twin, that spontaneously flicker into existence. They appear live for a fleeting instant and then annihilate each other, paying back the energy debt so quickly it is as if they never were. We know this is not just theory. The Casimir effect, where two metal plates placed extremely close together in a vacuum are pushed together by the pressure of these virtual particles outside them, provides direct experimental evidence. This quantum jitter is a fundamental property of reality. Now, scale this idea up to a cosmic level. What if, instead of a single particle pair, a quantum fluctuation occurred on a scale encompassing all of space and time? A fluctuation so vast that it borrowed enough energy to create not just a particle, but an entire universe's worth of them. In this scenario, the Big Bang was the moment this colossal bubble of space-time and matter popped into existence. The immense gravitational energy of all the matter in the universe is negative, and it is theorized that this negative energy could perfectly balance out the positive energy of the created mass, resulting in a net energy of zero. The universe in its entirety could be the ultimate free lunch, a vast and complex fluctuation from nothing that required no net energy to create. Our entire reality, with all its galaxies and stars, could be a stabilized quantum hiccup in an infinite and eternal nothingness. A something that emerged from a true void because, at the most fundamental level, absolute nothingness may be inherently unstable. This elegant solution to the matter-antimatter puzzle comes from a fundamental cosmic symmetry. At its heart are three core principles, CPT, which stand for charge, parity, and time. Charge conjugation means swapping every particle with its antimatter opposite. Parity is like looking at the universe in a mirror, flipping left and right. And time reversal is simply running the clock backwards. For decades, physicists believed that our universe was perfectly symmetric under the combined application of all three of these transformations. If you took our universe, replaced all matter with antimatter, viewed it in a mirror, and ran time in reverse, the laws of physics would behave exactly the same. It is a perfect, unbreakable symmetry, yet we observe a universe filled with matter and almost no antimatter. If CPT symmetry is truly perfect, how can this be? The answer proposed by this theory is as radical as it is beautiful. Perhaps our universe is only one half of the complete picture. We are the matter half, expanding forward in time from the Big Bang. But what if there is another universe, a perfect mirror, born from the same initial event? This would be an antimatter universe, identical to ours in every way, but with one crucial difference. From our perspective, it is evolving backwards in time. This is the concept of the biverse. Think of the Big Bang not as a single starting pistol, but as a central point of symmetry. Two universes blossomed from this point, like two sides of the same coin being flipped into existence. Our arrow of time points away from that moment into the future. The other universe's arrow of time, from our point of view, points away from that moment into the past. In that sister cosmos, what we call the future is their past, and their stars are made of antimatter. This elegantly preserves the sacred CPT symmetry. The total system, the entire biverse, is perfectly balanced. The overwhelming dominance of matter in our cosmic neighborhood is not a violation of physics. It is simply an observational artifact because we are trapped on our side of the mirror. We only see the matter moving forward. The antimatter required for balance is all contained in the other universe, flowing in the opposite temporal direction. For the very first particles, this model offers a stunningly simple origin story. There was no need for a special 1 in 10 billion imbalance to be baked in at the beginning. The initial condition could have been perfectly symmetric with equal amounts of matter and antimatter. Our universe got the matter and the other universe got the antimatter. Both sets of particles were created in perfect, symmetrical lockstep, one destined to move forward and build our future, the other destined to move backward and build its own. We are not the lucky survivors of a near-total annihilation. We are one half of a grand cosmic duality, forever linked to an antimatter twin we can never see. Our own cosmos might be the interior of a black hole born in a higher dimensional reality. This is the black hole genesis theory, a speculative but compelling idea that reimagines the Big Bang as a cosmic rebirth event. Within the heart of a black hole in some parent universe lies a singularity, a point where known physics breaks down and density becomes infinite. We have always assumed that matter falling into this abyss is crushed out of existence, its information lost forever. But what if that is not the end of the story? The extreme physics at the singularity could have acted not as a final grave, but as a cosmic trigger. The unimaginable pressure and density might have rebounded, sparking a new, rapid expansion of space within the black hole itself. In this scenario, our entire universe, from the first particle to the most distant galaxy, exists inside the event horizon of a black hole we can never see. The matter that fell into that progenitor black hole was not destroyed. It was transformed. The first particles of our reality, the initial quarks and electrons, were not created from nothing. They are the recycled remains of stars, planets, and who knows what else from a universe that existed before our own. Their fundamental properties may have been remixed in the fiery crucible of the singularity, giving our cosmos its unique set of physical laws and constants. We are not the first universe, but the offspring of another, living in the hidden interior of a cosmic tomb that became a cradle. This cosmic genesis of particles, however, was not yet complete. A final, crucial ingredient was missing, one that would define the very nature of reality from that moment forward. That ingredient is mass, and its origin story is tied to one of the most important fields in the universe, the Higgs field. For a fleeting instant after the Big Bang, all the particles we know raced through the cosmos at the speed of light, completely massless. The electromagnetic force and the weak nuclear force were unified, two aspects of a single, elegant interaction. But as the universe expanded and cooled past a critical temperature, everything changed. This was the electroweak phase transition, a moment when the cosmos underwent a profound shift. The Higgs field, which had been in a high-energy, symmetric state, suddenly dropped to its lowest energy configuration. It was as if a cosmic switch had been flipped. This new state of the Higgs field was not zero. It was a constant, non-zero value that permeated all of space, an invisible cosmic molasses that filled the void. As other particles moved through this suddenly active field, they interacted with it. The strength of that interaction determined how much they would slow down, how much they would resist being pushed, in other words, how much mass they would acquire. Think of a famous person trying to walk through a crowded room. They are constantly stopped for handshakes and photos, their progress slowed by the interactions. A less famous person, interacting less, moves through the same room with much greater ease. In this analogy, the room is the Higgs field. Particles like the top quark, which interact very strongly, became immensely heavy. Particles like the electron, with a weaker interaction, ended up with very little mass, and particles like the photon, which do not interact with the Higgs field at all, remained utterly massless, forever traveling at the speed of light. This single event, this turning on of mass, was a pivotal breaking of symmetry. It ripped apart the unified electroweak force, cleaving it into the distinct electromagnetic force and the weak nuclear force we observe today. This is why the weak force has such a short range, carried by massive W and Z bosons bogged down by the Higgs field, while electromagnetism, carried by the massless photon, reaches across the universe. Without this phase transition, without the Higgs field giving mass to the fundamental building blocks, there would be no atoms, no chemistry, no structures of any kind. The universe would be a formless, eternal flash of light-speed particles, unable to clump together to form the stars, planets, or life itself. The first stable particles, as we know them, were truly born in that moment, their identities and destinies sealed by an invisible field that gave them weight and substance. The profound silence of the universe is broken by the whispers of a ghost. While the Higgs field gave mass to known particles, a deeper mystery lingered in the quantum laws governing the strong nuclear force. This force, which binds quarks into protons and neutrons, possesses a curious quirk. The equations allow for a parameter that would make the neutron inherently lopsided, giving it a measurable electric dipole moment. Yet experiment after experiment has found the neutron to be perfectly symmetrical. This glaring absence of an expected effect is known as the strong CP problem. To resolve this puzzle, physicists proposed a new fundamental symmetry of nature. The elegant solution predicted the existence of a new particle, the action. This hypothetical entity is unlike any other. It is fantastically light, billions of times lighter than an electron, and it interacts with ordinary matter only with the faintest of whispers, making it incredibly difficult to detect. But its shy nature is precisely what makes it a superstar candidate for the universe's missing mass. Actions are a prime candidate for dark matter. In the hot, dense conditions of the early universe, actions would not have been produced in particle collisions like others. Instead, they are thought to have been born from a phase transition, a moment when a field associated with this new symmetry settled into its lowest energy state. As this field relaxed, it began to oscillate coherently across all of space, and these cosmic vibrations would have manifested as a vast, cold Bose-Einstein condensate of actions. This means these particles could have been among the very first stable entities to emerge, condensing out of the primordial energy long before atoms ever existed. They would have formed an invisible, frictionless ocean permeating the entire cosmos, a scaffold upon which the first galaxies would later coalesce. We are likely swimming through this ghostly sea right now, a relic from the universe's first moments that may hold the key to its largest structures. But the elegant promise of supersymmetry comes with its own cosmic complication, a puzzle known as the gravitino problem. If supersymmetry is a real feature of our universe, then for every known force-carrying particle, there must be a superpartner. The graviton, the hypothetical particle that carries the force of gravity, would be paired with the gravitino. This particle would be staggering in its implications, a bridge between the quantum world of particles and the large-scale geometry of spacetime. In the intense heat of the very early universe, gravitinos would have been produced in enormous quantities, constantly colliding and interacting with other particles. The problem is their lifespan and their staggering mass. Gravitinos are predicted to be incredibly heavy, and most importantly, they are unstable. They would have decayed into lighter particles as the cosmos cooled. But here is the catch: if they lived too long, if they decayed even a single second after the pivotal era of Big Bang nucleosynthesis, they would have unraveled the delicate process that forged the first atomic nuclei. Imagine the universe just a few minutes old, a perfectly tuned nuclear reactor beginning to fuse protons and neutrons into helium. Now, inject a flood of decaying gravitinos into this environment. Each decay would release a blast of high-energy radiation, shattering the fragile deuterium and helium nuclei as quickly as they could form. The entire primordial fusion process would be poisoned, leaving behind a universe with a completely different elemental composition than the one we observe. The fact that we live in a cosmos with exactly the right amounts of hydrogen and helium is powerful evidence that this did not happen. The gravitinos must have either been scarce, decayed almost instantly, or been so incredibly long-lived that they are still with us today as a component of dark matter. This cosmic constraint forces physicists to carefully sculpt their models of supersymmetry and the early universe. It tells us that the first moments of particle creation were governed by a set of rules so precise that even the existence of a hypothetical superpartner had to be carefully managed, lest its presence destroy the very foundations of our physical reality. But the search for the ultimate building block does not end with the quark. What if the particles we consider fundamental are themselves complex structures? This is the radical proposal of prion theory, a model suggesting that quarks and leptons are not indivisible points, but are instead made of smaller, more fundamental entities. Imagine our standard model of particles as a diverse and colorful Lego kit. We have many different shaped bricks, quarks, electrons, neutrinos, and more. Prion theory asks if these distinct bricks might themselves be assembled from a much smaller, universal set of connectors. In this vision, a quark and an electron would not be fundamentally different. They would simply be different combinations of the same few prionic building blocks, bound together by a new, ultra-powerful force. This would be a profound simplification, reducing the entire zoo of fundamental particles to just a handful of truly elementary components and their interactions. If this is true, then the story of the first particles changes completely. In the hot, dense aftermath of the Big Bang, the very first stable entities to emerge from the cooling energy would not have been quarks or electrons. They would have been prions. These primordial bits would have swarmed through the infant universe, colliding and combining under the influence of that powerful new force. The familiar particles of our world, the up quarks, down quarks, and electrons that built the first atoms, were not the pioneers. They were the second generation, assembled like complex molecules from a sea of more basic ingredients. The proton in every atom would then be a composite of a composite, a nested structure of reality reaching down to a deeper level. So why has no one ever found a prion? The challenges are immense. To bind prions into objects as small as a quark would require an unbelievable amount of energy, far beyond what our most powerful particle colliders can produce. It is like trying to see the individual grains of flour in a baked loaf of bread by hitting it with a hammer. You just get smaller crumbs, not the fundamental grain. Furthermore, the simple prion models developed in the 1970s and 80s struggled to explain all the properties of the particles they were trying to build, often predicting effects that our most precise experiments have never seen. Despite these hurdles, the conceptual appeal remains powerful. It suggests that our journey to the bottom of reality is not over, and that the true first particles, the ultimate seeds of all matter, may still be waiting to be discovered, hidden within the very heart of what we already know. While the Higgs field offers a compelling story for mass, it is not the only possible narrative. Another powerful idea, known as technicolor theory, proposes a radically different origin for this most fundamental property. This theory suggests that mass is not granted by a passive, omnipresent field, but is instead forged through a new, powerful fundamental force. The name itself is a play on words, referencing the strong nuclear force or quantum chromodynamics, which uses a property called color charge to bind quarks. Technicolor posits a similar but even stronger interaction that operates at a much higher energy scale. In this vision, the early universe was not waiting for the Higgs field to switch on. It was a turbulent arena dominated by this new technicolor force and a whole new family of fundamental particles called technifermions. These particles would have been to technicolor what quarks are to the strong force. In the extreme heat of the cosmos's first moments, these technifermions would have roamed freely, unbound and massless. But as the universe expanded and cooled, the technicolor force became overwhelming. Just as the strong force locks quarks together into protons and neutrons, the technicolor force would have seized these technifermions, binding them into composite particles known as technihadrons. It is the formation of these composites that generates mass dynamically, not through a molasses-like field, but through the raw binding energy of a powerful interaction. Think of it like a stretched spring. When the technifermions are free, the system has little energy, but when the technicolor force snaps them together, that binding represents a huge amount of stored energy. And since energy and mass are two sides of the same coin, that binding energy directly translates into the mass we observe for the particles we know, like the W and Z bosons. In this story, the W and Z bosons are not elementary particles slowed down by the Higgs. They are themselves composite objects, intricate bound states of technephomenes, their immense weight a direct result of the incredible force holding their components together. This provides a different path to breaking the electroweak symmetry, one driven by a powerful cosmic confining force rather than a cosmic phase transition. The echoes of this primeval technicolor interaction would be all around us, woven into the very mass of every particle that makes up our world, a testament to a fiercer, more dynamic origin story written in the first moments of time. Yet this delicate balance of creation and annihilation leaves us with a profound question. Why does anything exist at all? The survival of that 1 in 10 billion matter particle is not a minor detail, it is the single most important fact of our existence. This mystery is known as the puzzle of baryogenesis, the process that generated the slight excess of matter over antimatter in the very first moments. For this to happen, the universe had to satisfy three specific conditions, first outlined by the physicist Andrei Sakharov. The first condition is a violation of baryon number. Baryons are particles like protons and neutrons, and their number was thought to be a conserved quantity, meaning it could not change. For an imbalance to be created, some process had to actively produce more baryons than anti-baryons. The second condition is a violation of both charge symmetry and charge parity symmetry. This means that the laws of physics must treat particles differently from their antimatter counterparts, and they must also treat a mirror image version of the universe differently. If the universe were perfectly symmetrical in these ways, matter and antimatter would always be produced and destroyed in perfect, equal amounts, leaving nothing behind. The third and final condition is that all of this must have occurred outside of thermal equilibrium. The universe had to be in a state of upheaval, a moment of cosmic transition where processes could not simply reverse themselves. In a perfectly calm, balanced system, any budding asymmetry would immediately be erased. So, where and when did these three strict criteria come together? One compelling idea points to the grand unification epoch. As the strong, weak, and electromagnetic forces split apart, that violent breaking of symmetry could have provided the perfect out-of-equilibrium environment. The hypothetical X and Y bosons, those incredibly heavy messengers of the unified force, could have been the agents of change. Their decay might not have been symmetrical. Due to the subtle quirks of particle physics, these decays could have produced just a few more quarks than antiquarks, satisfying all three of Sakharov's conditions and seeding the universe with its vital matter surplus. Another possibility lies closer to home in the electroweak phase transition. When the Higgs field turned on and gave particles mass, it was another moment of dramatic cosmic change. If this transition was abrupt, like water freezing into ice rather than a smooth blending, it could have created the necessary departure from equilibrium. Bubbles of the new, broken symmetry phase would have expanded through the cosmos, and interactions at the walls of these bubbles could have preferentially generated more matter than antimatter. This would mean the origin of everything we see was not in the universe's very first instant, but a little later, tied to the moment particles acquired their mass. We are left with a universe that should, by all rights, be empty. The fact that we are here is proof that the primordial cosmos was not perfectly symmetrical. Some fundamental rule was skewed, some process favored existence over nothingness, and the echoes of that ancient bias are written into every atom of our being. Another invisible actor may have stalked the early universe, one born from the very fabric of its violent birth. The primordial black hole hypothesis suggests that in the first chaotic second, pockets of space could have become so intensely dense that they collapsed directly under their own gravity. These were not the stellar mass black holes formed from dying stars, which came much later. These were microscopic singularities, some as small as a single atom, yet containing the mass of an entire mountain. If the density fluctuations left by cosmic inflation were just a little more pronounced in certain spots, space itself could have pinched off, stitching these bizarre objects directly into the cosmos. They would have been incredibly numerous, a hidden population of gravitational ghosts weaving through the seething particle soup. Their most profound role could be as the long-sought dark matter. While other candidates like WIMP or actions are hypothetical particles, primordial black holes are a simple and elegant solution. They are just matter, albeit matter in its most extreme and invisible form. A vast collection of these tiny, ancient black holes could easily account for the gravitational glue that holds galaxies together without emitting a single photon of light. But their story does not end there. According to Stephen Hawking's famous theory, black holes are not entirely black. They slowly leak energy, emitting a faint glow of particles now known as Hawking radiation. For a stellar mass black hole, this process is agonizingly slow, taking longer than the current age of the universe to even make a dent. But for a primordial black hole with the mass of a mountain, the story is completely different. Its tiny size means its evaporation would be incredibly violent and fast. Over the billions of years since the Big Bang, the smallest of these black holes would have undergone a spectacular death. As they evaporated, they would not have faded quietly. In their final moments, they would have unleashed a torrent of particles and radiation back into the cosmos. This means that these primordial objects were not just passive dark matter. They were dynamic cosmic engines, recycling their mass back into the particle population of the young universe. Their deaths could have injected energy, influenced the formation of the first structures, and even provided a background of radiation that subtly shaped the universe's evolution. We are left to wonder if the particles that make up our world today were not all forged in the initial fireball, but some were spit out a second time from the dying gasps of these most ancient and mysterious gravitational tombs. These spin networks form the cosmic alphabet of reality, a language written in loops of space. In loop quantum gravity, the universe is not a smooth, continuous sheet. It is a vast, evolving web of these interconnected nodes and links, a tapestry woven from the smallest possible quanta of volume and area. Each link in this network carries a fundamental property called spin, a quantum number that essentially defines how much space is contained in that connection. The nodes where the links meet represent the discrete volumes of space themselves, but this is not a static picture. The network evolves, changing its configuration over time in a process governed by the rules of quantum mechanics. Links can be created or destroyed, nodes can merge or split, and the entire structure pulses with a dynamic, ever-changing geometry. This is where the concept of a particle undergoes a breathtaking transformation. In this framework, what we call a particle, like an electron or a quark, may not be a tiny dot moving through space. Instead, it could be a specific pattern of excitation, a particular vibration or distortion, traveling through the spin network itself. Imagine the fabric of space as a vast, calm lake. A particle would not be a speck of dust sitting on the water. It would be a ripple moving across its surface. The ripple is not separate from the water. It is a specific, organized motion of the water itself. In the same way, an electron might be a particular, stable pattern of twists and turns propagating through the woven geometry of the spin network. Its properties, its mass, its charge, and its spin would all be determined by the exact nature of this geometric knot as it travels. This suggests that the very first particles were not things that appeared in the universe. They were the universe expressing itself in localized, stable vibrations. When we peer down to the most fundamental level, we are not finding smaller and smaller billiard balls. We are finding intricate patterns in the architecture of space and time, a cosmic choreography where the dancers and the dance floor are one and the same. The smooth, continuous universe we perceive may be a grand illusion. Causal set theory offers a radically minimalist vision, proposing that reality is not a flowing river of space and time, but a growing collection of discrete moments like beads on an ever-lengthening string. In this framework, the cosmos is built from a set of fundamental points, each representing a single event. These points are not scattered randomly. They are connected in a vast network by a single, profound relationship, causality. One point is connected to another if it can influence it, if it lies in its past. The entire history of the universe, from the Big Bang to this very moment, is encoded in this web of cause and effect. There is no pre-existing stage of space and time for these events to play out upon. The stage itself emerges from the pattern of their connections. The familiar, smooth dimensions of space and the steady flow of time are not fundamental. They are approximate, large-scale properties that arise from the immense complexity of this underlying causal network, much like the smooth shape of a tree emerges from the intricate arrangement of countless tiny leaves and branches. Within this starkly elegant picture, how do particles come to be? They are not foreign objects inserted into space. Particles, with all their properties like mass and charge, are understood as specific, stable patterns within the growing causal set. Think of the set as a limitless sheet of graph paper that is constantly generating new points. A particle like an electron would be a particular, self-sustaining sequence of points, a persistent motif or a rhythmic vibration that propagates through the network as it grows. Its existence is not a given from the start, it is a consequence of the set's specific growth process. This leads to a profound new narrative for the origin of the first particles. In the very beginning, the causal set was tiny, perhaps just a single point. As new points were added, they connected to the existing ones, building up the first fragments of causal structure. The very first stable patterns to crystallize from this nascent network would have been the primordial particles. They were not created in a single, fiery instant, but sequentially, one after another, as the universe literally grew enough connections to support their existence. The first quark, the first electron, emerged as the causal set reached a critical complexity, allowing these persistent vibrational patterns to lock into place for the first time. In this view, the first particles were not born in an explosion, but in a quiet, logical unfolding, the earliest stable notes in a symphony of causality that is still being composed. The quantum threads that bind particles across space may be far more than simple connections. A revolutionary idea known as the ER=EPR conjecture proposes a breathtaking link between the two most bizarre concepts in physics, quantum entanglement and wormholes. The EPR part, named for Einstein, Podolsky, and Rosen, describes entanglement, that spooky action at a distance where two particles remain intimately connected, their fates intertwined no matter how far apart they fly. The ER part from Einstein and Rosen describes a wormhole, a bridge or tunnel through the fabric of spacetime connecting two distant points. This conjecture boldly states that these are not two different phenomena, but two sides of the same coin. Every pair of entangled particles is connected by a tiny spacetime bridge, a wormhole too microscopic and unstable to ever traverse, but a fundamental geometric link nonetheless. In the first fiery moments of the cosmos, this idea takes on a cosmic significance. The universe was an incredibly dense, hot soup where every single particle was in close contact with every other. Under these conditions, it is possible that all particles were born into a state of total, universal entanglement. This was not a collection of separate pairs, but a single, deeply interconnected quantum network. As the universe expanded and cooled, this web of entanglement was not lost. According to the conjecture, it was literally woven into the geometry of the newborn spacetime. The quantum connections between those first particles defined the very structure of the expanding universe, dictating how space would stretch and curve. Think of it like a vast cosmic knitting project. The entangled particles are the loops of yarn on the needle, and as the knitting progresses, expanding into a sweater, the relationships between those initial loops determine the entire pattern of the final garment. The wormholes, those tiny space-time bridges, were the stitches holding the fabric of reality together. This offers a profound new origin story for the first particles. Their most fundamental property was not just their mass or charge, but their relationship to every other particle through this geometric entanglement. The cosmic web of galaxies we see today, with its vast filaments and empty voids, could be a ghostly, macroscopic imprint of that primordial quantum web, a frozen relic of the universe's first and most intimate connections. This primordial equilibrium was a state of perfect chaos. In the first searing moments, the universe was so intensely hot and dense that no particle could hold onto its identity for long. Photons, quarks, electrons, and neutrinos all existed in a frenzied, continuous dance, constantly colliding and transforming into one another. A high-energy photon could spontaneously spawn an electron and its antimatter twin, a positron, only for that pair to immediately annihilate back into pure light a moment later. Every process was reversible, and everything was in perfect, seething balance with everything else. It was a cosmic soup where the ingredients were endlessly boiling, merging, and separating again, all kept in a uniform, blistering sameness by the relentless pace of their interactions. This was thermal equilibrium, a state where the energy was so evenly distributed that the entire cosmos behaved like a single, ultra-hot substance with no distinct parts. But this perfect, chaotic balance was destined to be broken. The relentless expansion of the universe was the great disruptor, steadily lowering the temperature and stretching the fabric of space. As it cooled, it crossed critical thresholds where the rules of the game changed forever. The first major shift came when the energy of the average photon dropped below the level needed to create new particle-antiparticle pairs. Suddenly, the constant creation of matter from light ground to a halt. This was the moment of freeze-out. The particles that existed at that instant could no longer be recreated once they annihilated. For most matter and antimatter, this led to their mutual destruction. But for that tiny, vital surplus of particles, it meant survival. They were frozen into existence, their identities permanently locked in as the universe became too cold and too sparse to destroy or transform them. Think of it like a sudden frost settling over a bubbling pond. The bubbles, which were once constantly forming and popping, are now frozen in place, their fleeting forms made permanent. In the same way, the expanding cosmos cooled so quickly that the particle zoo we know today was effectively snap-frozen into reality. The stable protons, neutrons, and electrons that would go on to build atoms were not always there. They are the relics of that great cosmic chill, the survivors of a sudden departure from a perfect, fiery balance. Their very existence is a testament to a universe that fell out of equilibrium, preserving a specific set of building blocks from an infinite range of possibilities. The final theory brings us to the edge of modern physics and confronts us with a paradox that strikes at the heart of reality itself. This is the black hole information paradox, and its implications reach all the way back to the very first particles. According to the rules of quantum mechanics, information can never be truly destroyed. If you burn a book, the information within it seems lost, but in principle, every single letter could be recovered from the precise state of the smoke and ashes. The information is scrambled, but it is never erased. Black holes, however, posed a terrifying problem for this fundamental rule. When something falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. Stephen Hawking later showed that black holes slowly evaporate, radiating away their mass until they potentially disappear entirely. This Hawking radiation appears to be completely random, carrying no information about what fell in. So, when the black hole is gone, where did all that information go? If it is truly lost, then a cornerstone of quantum theory is broken. Most physicists now believe the information must be preserved, somehow encoded in the Hawking radiation itself, but we do not yet understand the mechanism. Now take this cosmic puzzle and project it backward onto the Big Bang. Our entire universe erupted from an ultra-dense state that shares a disturbing similarity with a black hole singularity. If information cannot be destroyed, then it also cannot be created from nothing. This leads to a staggering possibility. The information describing every single particle in our cosmos, every quark, every electron, every force that would ever interact, was not created at the moment of the Big Bang. It was already present, encoded in the initial conditions of that primordial singularity. The first particles did not pop into existence with random properties. Their identities, their masses, their charges were all predetermined by a pre-existing cosmic code. The universe did not invent its laws as it went along. It unfolded them according to a fixed, immutable script written in the language of information. Resolving the information paradox might therefore reveal the ultimate law that governed what those first particles could be. Perhaps there is a deeper principle, a conservation law for information that constrains the possible initial states of any universe. In this view, the specific set of particles we have, the entire zoo of the Standard Model, was not an accident. It was the only possible outcome that satisfied the universe's need to preserve information from its very first moment to its last. We are not just made of stardust, we are made of cosmic data, the physical manifestation of a story that began with a single, unimaginably dense bit of information, unfolding into the complex reality we experience today. Our journey began with a single, silent point containing the entirety of existence. From that profound singularity, we have traced the epic of creation through 30 distinct visions of reality's dawn. We watched as the universe inflated from a quantum speck, witnessed the shattering of perfect symmetries that gave us a world of matter, and saw quarks imprisoned in the first protons and neutrons. We ventured into the possibility of a multiverse where our particles are just one lucky draw in an infinite cosmic lottery. We reimagined reality as vibrating strings, explored universes born from collisions in higher dimensions, and even considered that we might be living inside a black hole. We saw particles emerge as knots in the fabric of space itself, as patterns in a growing causal set, and as the frozen remnants of a great annihilation. Each theory, from the elegant to the extravagant, represents a towering human achievement, a testament to our unyielding curiosity about where we came from. This quest to understand the universe's first particles is more than a scientific pursuit. It is one of humanity's grandest adventures, a story we are still writing with every new observation and every bold idea. The conversation does not end here. We want to know which of these theories resonates most with you. Does the cosmic hologram capture your imagination, or do you find the endless cycle of the Big Bounce more compelling? Share your thoughts in the comments below, and if you are hungry for more journeys to the edge of understanding, be sure to subscribe for our next deep dive into the mysteries of the cosmos.